So let's talk about suspicious coincidences when you're trying to figure out what a word means and Bayesian inference. So here's a situation. See a Dalmatian and someone says fep. Well, they see another Dalmatian. They say fep. See a third Dalmatian, fep. And a fourth Dalmatian, fep. Okay, so what's suspicious here is why is no other animal or kind of dog a fep? If fep can really label those other things, right? It's a suspicious coincidence that it always just happens to be a Dalmatian if in fact fep could mean those other things. And the more that fep continues not to label other things, it continues to only label Dalmatians, the more that this is growing support that fep really can't mean those other things. It really must refer to Dalmatians, right? So formal instantiation, when we think of this in terms of hypotheses and hypothesis spaces, has to do with your expectation about the data points you should be seeing if fep means one thing versus another. So let's consider two hypotheses. A more general hypothesis that fep can refer to any kind of dog, and a less general one that can only refer to Dalmatians. So if the more general hypothesis dog is correct, then we should expect to see some data that can only be accounted for by that more general hypothesis. We should expect to see a beagle labeled fep or a poodle labeled fep, right? These data would be incompatible with fep just referring to Dalmatian, right? So how do we implement that in Bayesian inference to get this sense of suspicious coincidence? So we're going to be a little bit more explicit about our two hypotheses. So dog, the more general one, is going to refer to, say, any of these 7 dogs, and the less general hypothesis Dalmatian is only going to refer to, say, those 2 Dalmatians of the objects labeled here. So a Bayesian model is going to assume the learner has some space of hypotheses, in this case H1 that fep means Dalmatian, H2 that fep means dog, each of which represents a possible explanation for how the data D in the child's intake were actually generated. Okay? So given that data, the model child's goal is to determine the probability of each possible hypothesis, that is the posterior, where it's the probability of the hypothesis H given the data D. Right? And we calculate it using our Bayesian inference, which involves these different components again. So the first one is the likelihood, the probability of the data given the hypothesis. And this basically is describing how compatible that hypothesis is with the data actually observed. Right? So let's consider this data intake. We have 2 data points, 2 Dalmatians, each of which has been labeled a fep. Okay, that's our data. So what's the probability of that data given each hypothesis? So for hypothesis 1, there are only 2 things in H1, and the probability of either of them showing up then is 1 out of 2, if fep can only refer to those 2 things. So Dalmatian number 1, 1 out of 2 chance. Dalmatian number 2, 1 out of 2 chance. Great. Total probability, since these are independent events, we just multiply, and we get the total likelihood to be 1 out of 4. For hypothesis 2, now there are 7 things, the 5 dogs and the 2 Dalmatians, all of which are dogs, right? So there are 7 possible things that fep could refer to if fep meant dog. And so pulling any one of them out, you have a 1 out of 7 chance. You pull any one of them out twice, you get 1 over 7 times 1 over 7, which gives you 1 out of 49. So our likelihood's vastly different. This is where we can see the suspicious coincidence effect. That is, it's a suspicious coincidence for H2 to generate these data compared with H1 because H1 is far more likely to. 1/4 versus 1/49, 1/4 is a lot bigger. Okay, and we can see the result of this when we actually finish the Bayesian inference calculation and compare the relative probabilities of these 2 hypotheses. So that was our likelihood. The prior is going to represent the probability of the hypothesis before any data have been encountered. This usually corresponds to some sense of how plausible the hypothesis is, or how biased you might be towards it a priori, irrespective of having seen any data yet. So if we just sort of give them equal probability, they're equally likely, then they each get uniform probability, which in this case, since we only have 2 hypotheses under consideration, is 1 over 2. All right, so likelihood on top, prior on the bottom. To get our Bayesian inference, the posterior is going to be proportional to the likelihood of the hypothesis times the prior of the hypothesis. We can really just get away with working with those 2 probabilities if we don't need to do any kind of exact probability calculation, so let's do that. So for hypothesis 1, we have 1/4 likelihood times 1/2 prior gives us 1/8. Hypothesis 2, 1/49 likelihood times 1/2 prior gives us 1/98. Okay, here we are then. The more specific hypothesis H1 that fep means Dalmatian is over 10 times as probable as the more general hypothesis H2 that fep means dog, given these data which are actually compatible with both.